Hello everybody, and welcome to our video on the mean value theorem. So we're actually going to cover two extremely important theorems in this video. First one we're going to cover is Rolle's theorem. So let's go ahead and just get started. Let f be a function that satisfies the following three hypotheses. 1. F is continuous on the closed interval from a to b. 2. F is differentiable on the open interval from a to b. And 3. F of a is equal to f of b. Then, there will be a number c in the interval from a to b such that f prime of c equals 0. Okay, so let's just take a look at this picture, and I think it illustrates the idea pretty clearly. You have a function whose starting and end point over the interval have the same y value. That function is either going to go up or down unless it's a constant valued function. It's going to go up or down, and at some point, in order to reach that point again, it's got to turn around. And assuming it's differentiable in that interval, it's going to do so smoothly, let's say. And hence, you'll get a location like this, where the derivative is equal to 0 as the curve turns back to the other point. Okay, so how can we actually prove this? Well, we're going to do that by contradiction. So, in other words, we're going to assume the opposite of what we want, and then show that that causes an impossible conclusion. So we're going to assume that there is no number c in the interval from a to b such that f prime of c is 0. So we're assuming all the other conditions are met, function is continuous and differentiable, but that there is no c that makes the derivative 0 in the interval. Well, since f is continuous on a closed interval, it must have both an absolute minimum and an absolute maximum on that interval. This is by the extreme value theorem. And if the minimum is at, let's say, z in the interval from a to b, then Fermat's theorem tells us that since it's differentiable, f prime of z must be 0. So, it's got a minimum. If that minimum is inside the interval, then the derivative at that point is 0, but that would contradict our assumption. So that tells us that the minimum must not occur inside the interval from a to b. Okay, well, likewise, we can make the same exact argument. Let's say there must be a maximum on the interval by the extreme value theorem. And if that maximum occurs in the interval from a to b, then f prime of z would be 0, which again, we're assuming that there's no point where f prime is 0. So the absolute maximum would not be able to occur inside the interval from a to b. Therefore, both the maximum and minimum must occur on the endpoints, but f of a equals f of b, therefore the function must be a constant. But the derivative of a constant function is 0, which contradicts our assumption that f prime of x was never 0. So, we've checked all of the possible circumstances that could occur, right? We said, well, there can't be minimums inside the interval. There can't be maximums inside the interval. And if the minimums or maximums were on the endpoints, then the function would be a constant, but then the derivative would be 0. So that again contradicts our assumption that f prime of x is not 0. So there must be some c in the interval from a to b for which f prime of c equals 0. Okay, so let's go ahead and move on. We're going to find somewhere to apply this theorem. Okay, so here we've got show that x to the 5th power plus e to the x equals 0 has exactly one root. Well, in order to show that it has at least one root, we can use the intermediate value theorem, which we've done before, and we're going to do again. So this word exactly is very particular, right? So in order to show that something has exactly, we have to show that it has at least one and only 1. So for the at least part, we're going to go back to using the intermediate value theorem from before. So we're going to let f of x be the function, x to the 5th plus e to the x. And then we're going to just try plugging in some numbers, and we can make educated guesses here. So let's say, let's take a look at f of 0. Okay, that gives me 0 plus e to the 0, which is 1. And I'd like a negative value because I want to show that it has to equal 0 somewhere. So let's try negative 1. Then I get negative 1 to the 5th power, that's negative 1, plus e to the negative 1st power, that's negative 1 plus 1 over e. But 1 over e is like 1 divided by 2.7-ish, something like that, right? So that's about 1/3. So this is minus 1 plus 1/3. This is definitely less than 0, which is the part that's important. Okay, so with that out of the way, we know we have a positive value for the function, we have a negative value, and that implies that there exists a, let's call it a, in the interval from -1 to 0, such that, so remember, I know I don't use this notation very often, but that backwards e means there exists an a in the interval from -1 to 0, such that f of a equals 0 by the intermediate value theorem. Okay, so that tells us that this has at least one root. X to the 5th plus e to the x equal to 0 has at least one root. But now we want to show that it doesn't have any others. There's only one solution to the equation. Okay, so we'll do this by contradiction. So we will assume to the contrary. That there is another number b. So I mean specifically another number as in one that isn't equal to a, such that f of b is also 0. And let's just see what happens if that's true. So this function, x to the 5th plus e to the x, is continuous and differentiable everywhere. So since f is continuous and differentiable everywhere, and f of a equals f of b, then there exists a c in the interval from -1 to 1. Now, technically c has to be between a and b, but I said -1 to 1, that should be -1 to 0. Technically, C, this is actually stronger. C has to be between whatever A and B are. But we don't know what A and B are. We know that A and B are within the interval from -1 to 0. So if C is between A and B, then C is certainly between -1 and 0. There. So there is a c in that interval from -1 to 0 such that f prime of c equals 0. But when we look at the derivative of this function, we get 5x to the fourth plus e to the x. And e to the x is always greater than 0, and 5x to the fourth is at least 0 or greater, so this whole thing is bigger than 0. So f prime of c cannot be 0. Okay, well, what does that mean? Well, everything we've done here has been logically consistent and true, except for this assumption that f of b could be equal to 0. So there is no b such that f of b equals 0. So that implies there is only one root. All right, we showed above that there was at least one root. We showed here that if there was a second root, it would create a contradiction. And so there must be only the one root. Now, let's say you are trying to solve an equation for some sort of application. Why is it very valuable to be able to do this kind of work? Well, if you're trying to solve an equation and you want to know, is it worth my time? Well, how do you know if it's worth your time? There's got to be solutions for it to be worth your time. And then you want to know how many you have to track down, right? So that's really what it comes down to. There are approximation methods we can use. They are usually more time consuming. So if we can actually show, hey, we know there's for sure a solution and there's only one unique solution, then it's more likely to be worth your time to go down the path of using approximation techniques to solve for it. Okay, well, now that we're done with that one, let's go ahead and move on to the mean value theorem. Mean is in average, not as in not very nice. Okay, so the mean value theorem is kind of a generalization of Rolle's theorem. So it's actually a stronger statement than Rolle's theorem, but we tend to use it in slightly different circumstances. So mean value theorem states simply, let f be a function that satisfies that 1, f is continuous on the closed interval from a to b, and 2, f is differentiable on the open interval from a to b. Then there exists a c in the interval from a to b, such that f prime of c equals f of b minus f of a over b minus a. Or equivalently, f prime of c times b minus a equals f of b minus f of a, which we would get from just multiplying the denominator across. So all this says is that if you've got this function at a on the interval from a to b, and here's f of a and here's f of b, it says that at some point on the curve, the slope of the tangent line is the same as the slope of the secant line between the two endpoints. That's all it says. Now, this may seem a little bit different than Rolle's theorem, but if we just take a look at Rolle's theorem again, well, if f of a is equal to f of b, then the slope of the secant line is 0. And we said Rolle's theorem says that the derivative at some point is also 0. So it's really saying exactly the same thing, but the mean value theorem is a more general version of that statement. Okay, so the proof for this is a little tricky in the sense that it uses a really clever trick, and it's not the kind of trick I would, expect a student to come up with off the top of their head, but it is a pretty sensible trick when you think about it. So what we're going to do first is cleverly define a new function. And so this function here, h of x, that we're defining is going to be f of x minus t of x. But what is t of x here? Well, t of x is just going to be the equation for the secant line that we have here. So we're looking at the secant line, and we're taking the point A, f of A, that's this point, and we're taking the slope of the secant line, which is f of B minus f of A over B minus A, that's rise over run. Now, why are we taking this function? Well, we're creating this function because it's going to allow us to apply Rolle's theorem to get this desired conclusion. So what's the conclusion? Well, what's the condition for Rolle's theorem? We need the function to be equal at the endpoints. And what do we see? We see that this line has the same value as f at the endpoints. So we know at least that by using that secant line, we'll get the same value for f and for here, and f minus itself, whatever y value we get minus itself, is going to be 0, right? So we're going to show that rigorously in a moment. Okay, so let's check the conditions for Rolle's theorem. First, h is continuous, because this is just a continuous function minus a continuous function, and sums and differences of continuous functions are continuous. And same, we could say that this is differentiable, since f of x is differentiable and linear functions are differentiable. So it's continuous and it's differentiable. And now let's see what happens at the endpoints for this new function. Plug in a into h, you get f of a minus this. And when you plug in a, you get a minus a is 0. So this thing is going to be 0, and f of a minus f of a is 0. Likewise, here, got f of b. Well, this one's a little trickier, because here, we don't just get 0, we don't have the a minus a, so it doesn't work quite as nicely. But we get b minus a over b minus a, so these cancel. And we get left with f of b minus, parentheses, f of b minus f of a plus f of a. The f of a's cancel, the f of b's cancel, and we get 0. So for h of a and h of b, we got 0 for both of these. So h of a equals h of b. And what does that tell us? That tells us that there exists a c such that h prime of c equals 0. Okay, so remember, h of x is just this function here. So h prime of x is the derivative of the difference. It's f prime of x minus. When we do this derivative, this is just a constant times x. And when you distribute it, the rest of this stuff is constants. So all these constants, when you take the derivative, will be 0. When you take the derivative of this times x, you're just going to get left with the f of b minus f of a over b minus a. So going back, that tells us that at this c value, where h prime of c equals 0, f prime of c minus f of b minus f of a over b minus a equals 0. Move this to the other side of the equation, and we get that f prime of c equals the slope of the secant line, f of b minus f of a over b minus a. Okay, so that one's a little bit tricky, but again, really just boils down to, hey, create a new function that's really just f of x minus the equation for the secant line, apply Rolle's theorem to that, and the result we were hoping for just pops right out. Okay, so now we're going to take a look at an example where we are going to verify that the function satisfies the mean value theorem, and then we're going to find all numbers c that satisfy the conclusion. So we're looking at f of x equal to 2x cubed plus 4x squared minus 10x on the interval from -1 to 5. Okay, so mean value theorem. Well, what are the conditions? It's got to be continuous and differentiable. But f is a polynomial. Switch to blue here. F is a polynomial. So it is continuous and differentiable everywhere. Okay, well, that part's easy enough. So that tells us that there exists a c such that f prime of c equals f of 5 minus f of -1 over 5 minus -1. Now we want to solve for c here. So that means we're going to have to take our derivative here, and then we're going to have to find these values and just plug everything in, right? So let's go ahead and start by first finding the derivative. So f prime of x is 6x squared plus 8x minus 10. Now f of 5 is what we get when we plug 5 into our function. So 2 times 5 cubed plus 4 times 5 squared minus 10 times 5. Okay, so that's 2 times 125, that's 250, plus 4 times 25, that's 100, minus 50. That's going to be 350 minus 50 is 300. Now f of -1, that's 2 times -1 cubed, plus 4 times -1 squared, minus 10 times -1. That's 2 times -1, that's -2, plus 4, plus 10, that's going to be 12. Okay, so in other words, once we plug this stuff in, f prime of c, just replace c in my formula here, 6c squared plus 8c minus 10. And then we get 300 minus 12 divided by 6. All right, this gives us 6c squared plus 8c minus 10 equals, that'll be 288 over 6. Okay, and 288 divided by 6, what do we get there? 288 divided by 6 is 48. So we get 6c squared plus 8c minus 10 equals 48. So now if I subtract 48, I get 6c squared plus 8c minus 58 equals 0. So now if I want to solve for the values of c, we can just apply the quadratic formula. So we get -8 plus or minus the square root of 8 squared minus 4 times times 6 times -58 divided by 2 times 6. That's -8 plus or minus. All right, we'll just plug this whole expression into the calculator real quick and knock that one out super fast. 4 times 6 times -58. Get 1456 divided by 12. Okay, so that's our two answers. Now, we can write this out separately. C1 equals -8 plus the square root over 12. C2 equals -8 minus the square root. Now, the only thing here is to check which one is in the interval. So we actually do need to approximate these. Normally, I would say, hey, just leave this. Don't plug it into your calculator. Who cares? It's fine. But because of the fact that the question is specifically asking us to find the ones that satisfy the mean value theorem, which means that the value we find should be in the interval from -1 to 5, we actually do then need to check that the value is in the correct interval. So we get -8 plus that square root divided by 12. And I get approximately 2.51. So that seems fine. And then we get -8 minus that square root. And that's approximately -3.85. And our interval was from -1 to 5. So that one is not in the interval. So this is the only one that's in the interval. Okay, so that's it for that one. Let's go ahead and move on to another quick theorem. If f prime of x equals 0 for all x in an interval from a to b, then f is a constant on the interval from a to b. So proof, let x1 and x2 be in the interval ab, such that x1 is less than x2. Then since f is differentiable on the interval from a to b, it must be differentiable on the interval from x1 to x2 and continuous on that interval. Therefore, the mean value theorem applies, and f of x2 minus f of x1 should be equal to f prime of c times x2 minus x1 for some c in the interval. And if f prime of c is 0, that means f of x2 minus f of x1 is 0. So f of x2 equals f of x1, which is the definition of a constant function. Of course, this should make sense. We know that if f is a constant function, then its derivative is 0. So we're just proving the opposite here, which is to say that the only functions whose derivatives are always 0 are the constant functions. Okay, so now a corollary here is that if f prime of x equals g prime of x for all x in an interval from a to b, then f minus g is a constant. That is, f of x equals g of x plus c, where c is a constant. So the proof is just to apply this theorem here, which is to say that if I take f minus g of x prime, that's f prime of x minus g prime of x. And if these two things are equal, then this is 0. And if this is 0, f minus g is a constant function. And if f minus g is a constant function, then if I move the g over, I get f equals g plus c. So this may seem like a really small little, like a thumbnail problem, like a no big deal, but this idea is going to be really, really important. Later on, we're going to use this all the time. If you have two derivatives that are equal, then the original functions only differ by a constant value. So that's a very important thing to keep in the back of your head. We won't use it a ton right now, but it won't be long before it comes up pretty frequently. Okay. So let's take a look at this this example here. I shouldn't say last example. It's not our last example, but we're getting there. If f of 2 equals 5 and f prime of x is greater than or equal to 2 for x between 2 and 7, so implied here is that f is differentiable. So here f is differentiable. And we know that differentiable functions are also continuous. So we immediately know if this thing is differentiable, we know that it's continuous as well. So if f of 2 equals 5 and f prime of x is greater than or equal to 2 for x between 2 and 7, how small can f of 7 possibly be? Show this rigorously. So a lot of times I'll have students take some weird approaches to this, and there are some cases, not most of them, but some cases where you can kind of get lucky and make an educated guess towards the answer. But if I'm asking you this question, I really want you to show this using these tools rigorously. So, how can I show this? Well, I'm looking for some way to relate the values of the function to the derivative of the function. So what do I know? Since f is differentiable and continuous, that implies that there exists a c in the interval from 2 to 7, such that, actually I should say the open interval from 2 to 7, such that f prime of c equals f of 7 minus f of 2 over 7 minus 2. But f prime of c is greater than or equal to 2. So that implies that this expression is greater than or equal to 2, because it's equal to f prime of c. And we know that f of 2 is 5, and 7 minus 2 down here is 5. So now we've got the inequality 2 is less than or equal to f of 7 minus 5 over 5. Multiply the 5 across. We get f of 7 minus 5 is greater than or equal to 10. Add the 5. And that implies that f of 7 is greater than or equal to 15. So, in other words, how small can f of 7 be? 15, right? That's the answer. That is the smallest number we can get for f of 7. All right, now this is really our last example, and this is kind of a theorem as well. So suppose that f and g are continuous on an interval from a to b, differentiable on the open interval from a to b, f of a equals g of a, and f prime of x is less than g prime of x for x on the interval from a to b. Prove that f of b is less than g of b. So we're going to use a clever trick here. We're going to apply the mean value theorem to this function h of x equals f of x minus g of x. So the first thing is, let's see what we get on our endpoints for this function. So we get h of a. Well, what's h of a? It's f of a minus g of a. But f of a and g of a are equal, so when I subtract them, I get 0. And what's h of b? Well, that's just f of b minus g of b. Now, what else do we know? We know that f and g are continuous and differentiable. So, since f and g are differentiable and continuous, so continuous on the interval from a to b, and differentiable on the open interval, that implies that their difference, h, is as well. So h is continuous and differentiable, and then that implies, by the mean value theorem, that there exists a c in the interval from a to b, such that h prime of c is equal to h of b minus h of a divided by b minus a. But what do we know here? Well, we know that h prime of c is just f prime of c minus g prime of c. And what else do we know? We know that h of b is f of b minus f of a, or sorry, f of b minus g of b. Minus h of a, but h of a is just 0. Okay, so what else do we know? Well, we do know that f prime of c and g prime of c, well, what do we have? We have that g prime is bigger than f prime. And if g prime is bigger than f prime, and I'm subtracting g prime, that tells me that f prime of c minus g prime of c is negative. So if this is equal to this expression, that implies that f of b minus g of b over b minus a is also negative. And since b minus a is positive because b is larger than a, that implies f of b minus g of b is negative. And if I move the g across, I get that f of b is less than g of b. So basically, all we've done here is applied the mean value theorem to this difference function between the two. And then we just had to notice what is h prime of c and what is h of b minus h of a, and then do a little bit of algebra solving these inequalities. All right. Well, that's it for this video. Thank you for watching.